Good morning, everybody. This is Nicholas Zabaras, and we're continuing on our lectures on statistical computing and machine learning. So today we will revisit this topic of maximum likelihood estimation that we saw it in passing when we discuss different PDFs in earlier lectures. So we will most formally see this concept of maximum likelihood, and we will introduce a few more elements in the topic. So let's see what the topics for today will be. So we will introduce the likelihood function. I remind you that in this course we're looking at the likelihood as a function of the parameters rather than as a probability distribution. So we will talk a little bit about the frequentist and the Bayesian approaches, because the likelihood function comes in both of these settings. So we will talk a little bit about the differences, and also that way we can motivate some of the developments on Bayesian inference that we will do in a forthcoming lecture. So we will introduce formally the maximum likelihood estimator, and we will see it once more applied to the case of the univariate Gaussian, where our task will be to compute estimates for the mean and the variance of the Gaussian. We will use this opportunity for the univariate Gaussian to talk about what we call biased and unbiased estimators. So that would be a good place to introduce these concepts. And of course, I'm going to give you a few more examples. So we'll talk about the MLE estimates for the parameters of the Poisson distribution, and also for the multinomial distribution. I believe we have seen already this, but that's a good place to remind you how those formulas look like. I want also to do a connection between maximum likelihood estimators and least squares and linear algebra in general. And I can tell you, when we start doing regression problems, sort of the ideas that we will use before we do any Bayesian analysis will be to do maximum likelihood, and there we will see that the maximum likelihood estimators for the regression parameters effectively correspond to least squares solutions. So this is a good time for us to bring this idea early on in our course. We'll also extend the ideas from the univariate Gaussian to the multivariate Gaussian. There is nothing really new the way the formulas look like, but the algebra is a little bit different because it will require differentiation with respect to matrices. So that's something you need to be used, because it's a common type of calculation that we do in machine learning. And we will finish with some relevant topics on how we compute maximum likelihood estimators sequentially. And what I mean here sequentially is, if we have one data point arriving at a time, can we use our previous estimate for our parameters based on all the previous n-1 points to move to the case where once we collect the nth point. So can we use the n-1 estimate to compute the estimate when we have all n points available, without having to reuse all the points explicitly from our previous data set, just using the previous estimator only? And I'm going to try, in the process of talking about this sequential estimation, we will see that some of the formulas look very similar to the formulas that someone gets in stochastic gradient descent. So this will be a good place to introduce the Robbins-Monro Algorithm and see how the Robbins-Monro Algorithm can be used for sequential estimator, for sequential estimation of the mean and the variance for both the univariate and the multivariate Gaussian. All right, so the goals for today's lecture are the following. So we need to understand how to compute maximum likelihood parameter estimates, in particularly for the univariate and the multivariate Gaussian. We need to understand what it means to have a biased and unbiased estimator of these parameters. We will also learn about this sequential estimation that I mentioned, and effectively I want you to get some starting working knowledge for what we call the Robbins-Monro Algorithm. Right? This is a very, very old algorithm, but is effectively the key algorithm that is being used in the training of complex systems such as neural networks, deep learning algorithms, etc., etc. It's one of the most popular algorithms for computing parameters, certainly based in maximum likelihood, but also regularized settings. Okay, the references for today, most of the material can again be found in Chris Bishop's machine learning book, and also Kevin Murphy contains lots of the discussion that you will see today, certainly in the context of these Gaussian MLE estimators. So let me remind you the Bayes rule, the way we're going to use it also later on in the context of Bayesian inference. So we have some data that I call them here D, that coming from some model that has some parameters theta. And what you see here is you see what we call the posterior of the parameters theta once we have observed the data D. So this is a direct application of Bayes formula. This P of D given theta is what we call the likelihood model. Is, you know, what is the likelihood of observing this data set D for the model that has this parameters theta, okay? And so if we will see examples if our model is Gaussian on, for example, how we compute this likelihood, and also I'm going to give you a few more cases so we can get a good sense on how the likelihood is computed. The only thing I'm going to say right now, when you compute the likelihood from observations of, let's say, points x1, x2, etc., we're going to assume that the probability of x1 given theta times the probability of x2 times theta, etc., is the product. This product is equal to the probability of the whole data set given theta. So basically we're going to assume that the observations x1, x2 are collected in an IID fashion. This distribution pi of theta that you see here is what we call the prior model on the parameters. So it's a probabilistic assumption on the parameters before we see any data. All right, so what we have here is we have the posterior equal to the likelihood times the prior, and the denominator I'm not going to bother in this lecture. The denominator doesn't depend on the parameters theta, and because our focus today is on computing an estimate for the parameters theta, we are not going to really bother about P of D. Okay. So what you need to remember from this slide effectively is the equation that you see with words on the bottom here that says the posterior is proportional to the likelihood times the prior. Now, we're going to cover the details of Bayesian inference in a forthcoming lecture, so you will hear about the same topics again in a more rigorous manner. But really what I wanted to do, at least for today's lecture, is I want to bring to discussion the frequentist versus the Bayesian approaches to inference. So first let me say that the likelihood is essential both for the Bayesian and the frequentist approaches. So what we will cover today, it is not a Bayesian approach, it's not a frequentist approach, it's a statistical approach that is used regardless what philosophy you follow. And but I need to say something, before we said, once we have the prior model and the likelihood, we get the posterior. So in the Bayesian setting, when we're going to be computing the parameters theta, really we're going to be computing the posterior of the parameters theta. And so effectively we're going to predict not just an estimate of the parameters theta, but also the uncertainty on theta. And this evaluation is being done through the posterior P of theta given D. So in a Bayesian setting, this parameter theta is taken to be as a random variable or a random vector, okay, depending on the dimensionality of theta. Now, in the frequentist approach, you will also see confidence intervals and error bars on the parameters theta. So the difference is that these error bars on the parameters theta are not induced because you have computed some posterior, but basically they express the uncertainties in a deterministic estimator for theta using different data sets. So you can imagine even if you do, let's say, maximum likelihood that we will discuss today, you use one data set, you get one parameter value, then you get another data set, you get another parameter value. The variability you observe on these deterministic estimators will consist, basically, will give you the error bars for the parameter theta. But in a frequent setting, theta is a deterministic variable. In a Bayesian setting, theta is a random variable. Let me also say that this data set D in a Bayesian setting, it's only one data set. We don't have multiple data sets to play around. There is only one data set D. If you want to produce uncertainties in the frequentist approach, obviously you need multiple data sets D, so you can compute your deterministic estimators for the parameters for each data set. And these data sets often go with the name bootstrap data sets. So for today, none of this is going to make a big difference, but certainly we're going to assume that we have only one data set D, and we're going to compute deterministic estimates for the parameters. So I am not going to bother to produce uncertainties on theta, even though we will talk about these estimates in the context of biased and unbiased estimators. And we will see this in a forthcoming slide. Okay, so that's all about the philosophical differences between the frequentist and the Bayesian approaches. So let me move directly to this maximum likelihood estimator, or simply written as MLE. So we're going to assume that we have a parametric model, and I denote here the probability density as pi of x given the parameters theta. So theta are the parameters of this probability model. So you can think if pi is a Gaussian, theta are the mean and the variance of that Gaussian. So there's no particular reason why I'm using pi here. It just, it all depends how you want to beautify the notation that you use. Some textbooks prefer to use pi instead of p, but in this course we will use one or the other depending on the lecture. So let's say that we're collecting IID data x1, x2, xn from this parametric model. So we're going to assume that this data are realizations of these capital Xj random variables, and because we collect this data in an independent fashion, I can write that the probability of the observations x1, x2, xn given theta is the product of pi of x1 given theta, pi of x2 given theta, etc. Pay attention here, the independence, but also the conditioning of all these events. It says given the parameter theta, and of course we will see that our goal today is to compute this parameter theta. So in this lecture and in the remaining of the course, we are going to take all of this data set and use a calligraphic D to represent it. So you will often see this notation for D that you see on the bottom, and also the likelihood written as this product of pi of xj given the parameters theta. Okay, so that's my likelihood, or in a more compact notation, the way that you see it here. And you can now guess that the maximum likelihood estimator is the parameters theta that maximize the likelihood. Okay. Now, often it is more convenient to work with logs. Certainly this is true when you work with Gaussians, because then the exponential can disappear and you can get nice quadratic forms. But there are also numerical reasons why you want to work with logs, because probabilities are very small numbers, so you don't want to have any numerical issues in your calculations. So theta MLE maximizes the likelihood, or maximizes the log likelihood, or if you prefer as an alternative, it minimizes the negative log likelihood that I denote here as L. And I wanted to introduce the negative log likelihood early on, because we will see later on when we pose estimation problems as minimizing some loss functions, this negative log likelihood is an appropriate loss function to use in many settings, and many extensions of further loss functions are effectively generalizing this capital L that you see here. But again, don't mix up things here. Maximizing directly the likelihood, or maximizing the log likelihood, or minimizing the negative log likelihood, they're all equivalent statements of the same MLE problem. Okay, so let me start giving you a few examples. So here is the univariate Gaussian, and we're going to assume that our main parameters are the mean mu and the variance sigma squared. So this is what we want to compute. So theta 1 is equal to mu, and theta 2 is equal to sigma squared. So what I want to do is I want to compute the negative log likelihood L. So if I multiply this, the exponential of the minus negative log likelihood would be given by this product. I only keep the parameters, all the terms that have the parameters theta 1 and theta 2. So any constants that come on the way, I don't really care. So maybe even in this equation I should indicate, for example, that here this is proportional rather than equal to what you see here. Well, actually it is correct as is, because I see the 2 pi here as well. But again, we only care only the terms that involve theta 1 and theta 2. So the negative log likelihood is given by this wonderful expression in the bottom. So we need to minimize this. The way you minimize, you're going to take the first derivative, you're going to set it equal to 0. I'm not going to bother to show the correct conditions for this minimization problem on the second derivative, but you have to trust me for this type of problems. There is one global minimizer of the negative log likelihood, and this is what we're going to compute by taking the gradient of L with respect to theta 1, theta 2, and set that equal to 0. So that's what we have here. And immediately you can see from the first term, setting this equal to 0, it will give you theta 1 being the summation of xj divided by n, and similarly you will get theta 2 being the summation of these error squares divided by n. So let me write these estimates. These are the MLE estimates for the mean and the MLE estimate for the variance. So you obviously agree that these estimates, not surprisingly, they're identical to the estimates for mu and sigma squared that we got using the law of large numbers, but now we can actually call them the MLE estimates. All right, so they are the estimates of mu and sigma squared that maximize the likelihood of the data under the parametric model that we're using in this problem. Okay, so let me summarize again the same formulas. You can see here a schematic where in my likelihood, each of these terms corresponds to the values of the Gaussian at these blue points. So you multiply all of those together. This is what gives you the likelihood. You see the log likelihood written here. And again, I remind you what the MLE estimates are for the mean and the variance. Now, previously when I showed you different plots of PDFs fitting data, effectively what we did is when somebody gives us data, for example, coming from a Gaussian, we compute the mean and the variance from these MLE estimates, and then we literally plot the Gaussian with those two parameters, the MLE parameters. And I remind you, we did this for this particular problem where we had this image with electromagnetic radiation. So every pixel are different values of electromagnetic radiation. So you can plot those in a histogram, but also you can actually approximate the distribution with this red Gaussian here, and this PDF, effectively the way it has been computed, we use the data to find the MLE estimates for mu and sigma square, and then we just plot a Gaussian with those MLE estimators. And I think we show a lot of plots like that. So remember, if you see some fitting with with a PDF, that PDF has been computed effectively by evaluating the MLE estimates for the parameters of the distribution. Okay, let me start saying a few things now about biased and unbiased estimators. So you remember we collected a bunch of data from a Gaussian, right? And we said that the estimator for the MLE estimator for the mean is the empirical mean of this data. Now, if you think here, if you repeat this experiment, right, x1, x2, xn, they're basically the values of random variables that are being sampled from this Gaussian. So in some sense, the MLE estimate, because it's x1 plus x2 plus xn divided by n, is also a random variable. And someone may ask, is the expectation of that with respect to the underlying distribution from where the data come, is that expected value equal to the true value mu? And the answer is yes. There's not much to derive here. If you take the MLE and you take the expectation, the definition of the MLE, and you take the expectation with respect to the underlying Gaussian from where the data come, you can see directly that the expectation of the MLE estimate of mu is the true mu, and this is what we call an unbiased estimator. So the MLE estimate for the mean is an unbiased estimator. Let's do the same thing for the variance. So if you take the variance and you plug in the MLE estimate that you use in your estimate for the MLE variance, so you're going to get the expectation of this big bracket. So you're going to have to expand this, and you're going to have to use the assumptions that xi's and xj's are IID coming from this Gaussian. So if you finish the expectation, I'm going to tell you actually what you need to complete this properly, but you do get that the expectation of the MLE estimate of sigma square is 1 minus 1 over n sigma square. So it doesn't come to be equal to the true variance of the Gaussian, which means that the MLE estimate for the variance is a biased estimator. Okay, and you can see that the variance through this MLE estimator is underestimated. Okay, we have minus 1 over n. Of course, this term as n goes to infinity is very small, but in settings where we have a small number of data set, the variance is underestimated, and this issue is not a trivial one, and we will see in the course, certainly when we do regression models, that effectively this issue is responsible for the overfitting that we will see again when we discuss regression models. Now, part of the issue why this came to be an unbiased estimator is in the calculation of the MLE estimate, we had to, you notice here, we have to compute the mean, and we use as an approximation for the mean, we use the sample mean, okay? So this is the MLE estimate for the mean and not the true mean, and this is what resulted in this biased estimator. So let me show you what type of calculations you will actually need to do this properly. So when you expand that big bracket that we had in the previous slide, if the xi and xj are such that I is not equal to j, because xi and xj are independent, then this expectation of this product will be the expectation of xi times the expectation of xj equal to mu squared. And when I and j are the same, then the second moment, the expectation of xi squared is the variance plus the mean square, where here we simply use the definition of the variance being the expectation of x squared minus the expectation of x, the whole thing squared. Okay? So this is actually the only thing that you will need to do the derivation. In statistics, because the MLE estimate that you see up here, all right, it's a biased one, you will often see in the literature an unbiased estimator for the variance, and that unbiased estimator actually, if I can give it to you, it looks like this, is similar in this form here, but instead of having 1 over n, it has 1 over n minus 1, okay? You notice that when we took the expectation of the MLE estimate for sigma square, what we got is we got n minus 1 over n. So if we actually define an unbiased sigma square estimate, that is the MLE estimate divided by this coefficient, obviously this will cancel with that when we take expectations, and the expectation of this sigma square unbiased is going to turn out to be sigma square, okay? So often in the literature, when you estimate sigma square for a Gaussian, this is what you use. You use 1 over n minus 1. Okay, so remember that. And also in your computer programs, often you will use 1 over n minus 1 to make this estimator unbiased. And again, computationally speaking, when n is very large, it makes no difference. So, but again, in small data settings, certainly small data sizes will be the case when we do Bayesian inference. This will come to be making a significant difference. Let me show you graphically the issue with this biased nature of the MLE estimator for sigma square, and this is a nice schematic that is coming out from Chris Bishop's PRML textbook. So consider that you have a true Gaussian that you see with this nice curve, all right, and you are doing let's say 3 experiments, and in each of them you collect 2 points. These are these 2 blue dots, okay? So 3 different cases, and in each case you're trying to fit, using your MLE estimates for mu and sigma squared, you're trying to fit a Gaussian. So obviously, let's say for this case, the mean will be somewhere here, all right, and the variance will be defined only by these 2 points. So effectively your Gaussian that you will get will be this red curve that you see here. And obviously you can immediately see, using 2 points, the variance is underestimated. And again, the variance is underestimated because the way you compute it is you compute it not with respect to the true mean that is here, but with respect to the sample mean that is there. Okay? So you repeat the experiment for the other 2 points. Again, the variance is underestimated, okay? You repeat it for the other 2 points, the variance underestimated. And you notice if you take the average of the MLE mean for the 3 cases, if you take the average of these 3 predictions, the mean is going to come to be very close to the mean of the true Gaussian. However, because the variances in all 3 cases are the same, the variance, when you average it, it will be again underestimated, and this is the standard problem with the biased nature of the MLE estimate of sigma square. So this is a wonderful picture to demonstrate these issues of MLE, and as I mentioned earlier, a lot of the problems with overfitting that we will get later on are directly related with these issues with MLE. And we will leave the discussion for that later in the course when we reach the point of discussing regression models. So let me move on to rapidly to a few other examples. So this is a Poisson distribution with parameter theta. Remember, the Poisson distribution takes integer values, it has only one parameter theta, and I remind you both the mean and the variance are given by theta. So obviously the question that somebody can ask now is, if I compute the MLE estimate for theta, is that going to be a good estimate for both the mean and the variance? Because you remember, theta is the same, is the mean and the variance for this distribution. So what is going to happen when I do take MLE estimates? So if you take a data set, you form the likelihood, okay? I just take the distribution for each of the points and multiply things together, that's the likelihood. You can actually take the negative log likelihood from that. You get a nice formula. Here you notice the first summation, for example, is theta times n, and this comes from this exponential e to the minus n theta. And remember, we take minus log likelihood, so this first summation comes from here, and this term comes from theta to nk, and of course we have this nk factorial coming here as well. Okay, so you can go and take derivatives with respect to theta, you set it equal to 0, and there is your answer. The answer is the expected one. Theta comes to be the empirical mean. And how about the variance? Is this a good estimate for the variance? And the only thing I'm going to tell you now is that if you compute the variance for the Poisson distribution using the law of large numbers, you will agree that this is what you get, right? If this is your mean, the law of large numbers is going to give you this, and certainly this has nothing to do with the MLE estimate that we computed. Okay, so you can immediately see sort of an ambiguity here, because we have one estimate for theta, but when it comes to the variance predicted by the law of large numbers, it doesn't agree with the MLE estimate of theta. That was not the case for the Gaussian, but now you can see we have a situation where the two things do not agree. Now you can do something else with the Poisson model. Maybe you forgot about it, but in an earlier lecture I told you that a good approximation of the Poisson model when theta is a large number is the Gaussian PDF with mean and variance equal to theta. So then somebody can say, can I do then an MLE estimate for theta but use the approximation of the Poisson model, which is the Gaussian model? So you can do that, and here is the Gaussian model with mean and variance, the same parameter as the Poisson model. So you can do MLE estimate for the Gaussian. Okay, here I have to do it. I cannot use the previous formulas because the mean and the variance are the same. So when I compute derivatives with respect to theta of the negative log likelihood, I'm going to get extra contributions from what I had before. So when you evaluate, you set this equal to 0, This is what you get, all right? So it comes out that the MLE estimate is equal to this, and again, unfortunately, it doesn't coincide with the result we get using the exact Poisson model. Okay, let me just finish these examples, these simple examples, and I'm going to remind you the MLE model that we had seen in an earlier lecture for the multinomial PDF. So remember, we have a coin with k different states, and in each experiment the probability of hitting state 1 is mu1, the probability of hitting state 2 is mu2, and this is mu subscript capital K. So we have this IID data. These are vectors that they're k-dimensional and only have one of their elements equal to 1 and all other elements equal to 0. So if you, so this is our probability model, the way we have seen it before. The sum of the mu k's, of course, is equal to 1. And if you use the sufficient statistics in n experiments that we represent them in an earlier lecture with mk. So mk is the number of times in the n experiments that the state k was on. All right, so it's the summation of the xn k's from n equal 1 to n. So if we use these sufficient statistics, the likelihood can be written with this nice form that you see in here. So if you compute the log likelihood, it will look like this, and you notice there is an extra term that penalizes this log likelihood with a Lagrange multiplier here, because I do have to satisfy the constraint that the sum of these mu's is equal to 1. So this penalized log likelihood has to be optimized with respect to the mu's, and I have capital K of those, and also with respect to the lambda. So if you take derivative with the lambda, this constraint is satisfied, and then you have derivatives with respect to mu. You will get one contribution from the second term and also one contribution from this term, which is actually going to be minus lambda when you take derivatives. And I can go ahead and give you the answer because we already have done, and the answer is the expected answer is that each of the mu i's is mi divided by n. So it's how many times my n experiments the state I was on. That defines, so that empirical average defines the probability mu I, defines the MLE estimate effectively for mu I. Okay, so we are done with these examples. So let me move to something that may look a little bit strange and out of touch or connection with what we have covered up to now in the lecture. So I want to make an early connection that somehow these MLE estimators for Gaussian models, they do actually turn out to be equivalent to least squares, and in many cases to what I call weighted least squares. So let me introduce a model, and I'm going to try not to discuss too much the motivation of this particular type of model, because we will see it in subsequent lectures. But let's say that, let me actually go backwards, and I'm going to start with an equation that is written on the follow-up slide. So let's say that x is related with some hidden variable z through this equation. X is equal to az. And az, so A is a matrix such that it matches the dimensions of x and z, and generally speaking, z is a lower dimensionality than capital X. Okay? So effectively, you can think that z is the hidden cause for x, right? X is high dimensional, z is a low dimensional, and we assume in this few slides that A is given. So in some sense, we're having sort of a dimensionality reduction model, right? We're expressing x in terms of some reduced z through the equation x equal to az. Now, when you do dimensionality reduction, obviously you lose some information, and we are going to assume that the noise that is introduced is given by this Gaussian that has a covariance gamma and has a mean 0. So effectively, if I can go now back to my previous slide, you can show that x is given from this Gaussian model, where the mean of this Gaussian model is a times z. Okay. In other ways, you can actually look alternatively this problem as you don't have direct observations of z. So what you have is you have some noisy observations of x, and these noisy observations come from the Gaussian that you see on the top. So the idea is, can you actually compute what this z is if I give you noisy observations x that are related with z through this Gaussian model that you see here? Again, the mean of this Gaussian model is az. There is some noise in the model, all right? That makes my observations to be noisy ones. So I have some samples of this and I want to compute z. And sort of, you can think of this as an inverse problem, where given noisy observations of this x0, all right, which are this capital X, we try to estimate what z is. So I'm going obviously to use maximum likelihood estimation for z. So what we're going to do is we're going to assume that we have a bunch of data sample for x, and this is my Gaussian model, right? This is the model that I started with. Gamma is assumed known, A is assumed known. So this is the probability model that I have. I'm collecting a bunch of data. I'm writing the likelihood like this, and then if I take the minus the negative log likelihood and expand all terms, I get this nice expression that you see in the bottom, that you notice because I had the mean of the Gaussian to be a times z, this negative log likelihood is a quadratic function in z, okay? Which means I can actually find the z by setting the derivatives of this equal to 0, and that is going to give me a linear system of equations that will allow me to compute z. So if you take the derivative of this with respect to z, set it 0, what you will get is this is the derivative. I am going to simplify it by getting rid of this summation and substituting as n times the sample mean, and here's the answer. So the unknown vector z is given by the solution of this linear system of equations, and for those that are familiar with least squares, you remember in least squares you always get a matrix on the left hand side that is of the form A transpose A. Okay, here this matrix is A transpose gamma inverse A. So for me it actually suffices to stop there and say that the maximum likelihood estimator, which is the z that solves this linear system of equations, is actually equivalent to a weighted least squares problem, and I call it again weighted because I have A transpose gamma inverse times A. If you want to see in an even simpler manner the weighted least squares nature of this problem, what actually I can do is I can write this negative log likelihood in a simplified form for the case that I only have one data point, and then it will be clear that that optimization problem, it is really a least squares problem. Okay, so let me do that just to simplify things. So I'm going to take that I only have one data point x, so my negative log likelihood is going to look like this. okay, for one data point. And so I am going to rewrite this. So I want to find the z that minimizes this negative log likelihood, and to write it in a nice least squares optimization problem, I am going to use the eigen decomposition for gamma. So I'm going to write gamma as the orthogonal matrix U of the eigenvectors times the diagonal elements of the eigenvalues times U transpose. I remind you, U is an orthogonal matrix, D is a diagonal matrix, and I can do this decomposition because my gamma matrix is symmetric. So when you take inverse of gamma and use the orthogonality property for U, and I'm not going to do all the algebra here, it comes out from this little calculation that gamma inverse is W transpose W, where W is given by this nice expression. So if you take this expression for gamma inverse W transpose W and you substitute it in the negative log likelihood, the negative log likelihood becomes this nice quadratic form, and immediately you recognize, right, if W was not there, minimizing this L2 norm of AZ minus X square, that's a least squares problem, and minimizing the weighted norm, so the L2 norm of W times AZ minus X is what I call a weighted least squares problem. So if this example doesn't resonate yet, I want you to remember that least squares problems and maximum likelihood estimators for the Gaussian models turn out to give you the same equations. Not approximately the same, exactly the same equations, okay? So any problems you may know with difficulties of least squares methods, really they are derived in a statistical setting from the issues we mentioned earlier with these MLE estimates. Okay, so we did the univariate case for the Gaussian, we derived the MLE estimates for mu and sigma square. Let me give you the MLE estimates for the mean and the covariance metrics for a multivariate Gaussian. You know, I can, I'm writing here the log likelihood, right, for an n number of data points xn, so there is nothing fancy about it, and I can even give you the answers that they practically are the same, written obviously in a vector and matrix form. They're the same as for the univariate case. So the MLE estimate for mu is the sample mean, the MLE estimate for sigma is the sample covariance. The question is, how do you get those, right? And to get those by maximizing the log likelihood or minimizing the negative log likelihood, you're going to have to take derivatives with respect to a matrix. And you may wonder, how do I take derivatives of, remember this is a scalar quantity here, right? This is, this function here is a scalar. How do you differentiate this with respect to the metrics? Well, you're going to have to use formulas that allow you to take derivatives with respect to matrices. And if you ask me where these formulas come from, think of taking derivatives with respect to each of the components of a matrix. So if you want to differentiate, let's say, a functional with respect to a matrix A, you can think of taking derivatives with respect to Aij, and that will give you the ij component of the gradient. And when you compute all of these components of the gradient, if you put them together, you will get a matrix, and these formulas actually directly give you the answer for that matrix when you take derivatives, okay? So if you take a scalar like we have here and you differentiate with respect, let's say, to sigma, because sigma is a matrix, you're going to get a matrix as an answer. Now, Things look complicated a little bit because here we have the log of a determinant of a symmetric matrix, and here of course we have the inverse of sigma. So how do we do all of this? So let's do the following trick first. If you take derivatives with respect to the mean mu, and I'm not going to do this here, it is almost straightforward to show that differentiating with respect to mu will give you the sample mean. Okay, so I'm not going to do this. I'm going to leave it as an exercise. So let's concentrate on the more difficult problem. So once we have the MLE estimate for mu that you saw in the earlier slide, we want to compute the MLE estimate for sigma. So we're going to have to take derivatives for sigma, but because there is sigma inverse here, it may be easier to take derivatives with respect to sigma inverse. Okay, so what I'm going to do is I am going to take derivatives with respect to sigma inverse. Now you may say, I don't see a sigma inverse here. I see the log of the determinant of sigma. Well, you know what? With a little bit of imagination, you know the determinant of the sigma inverse matrix is 1 over the determinant of the sigma matrix. So basically, actually, when I see here minus log of the determinant of sigma, you can actually write this as log of the determinant of sigma inverse. So effectively in both terms I can have sigma inverse. So let's do that. And again, you know, I'm going to do this rapidly, but when you go home and you can look at this derivation and convince yourselves that it does make sense, because you will need in many settings in machine learning to be able to do calculations like that. So let's take this term here, all right? So we're going to take derivatives with respect to the metric sigma inverse. So remember, this is a scalar. Derivative with respect to matrix has to give us a matrix. So minus the log of the determinant of sigma, I'm going to write it as log of sigma of the determinant of sigma inverse. And I'm going to use a formula that says when I differentiate the log of the determinant of a matrix A with respect to A, I get A minus transpose. So in my case, then I am going to get sigma inverse, another inverse transpose. So I'm going to get sigma transpose, which is equal to sigma. This formula that I'm using here, you will see it in the bottom of the slide when I am done. So effectively, the derivative of this gives us n over 2 times sigma. And let's compute the contribution from the second term. And here I'm going to use a trick that is almost universal in working with this Mahalanobis distance and this average, you know, over my data points n. So here is what the trick is. This whole summation is a scalar, right? Have a matrix times a vector, which is a vector times a row vector, you know, times a column vector gives you a scalar. So because this is a scalar, the trace of a scalar is it's equal to that scalar, and so I can put a trace to this whole summation outside, and nothing is going to change. And then I'm going to use a fundamental formula that says the trace of A times B is the trace of B times A. So if you take this to be A and sigma inverse times x minus mu to be B, I can write this as the trace of this times that. I can write it as the trace of sigma inverse times xn minus mu times xn minus mu transpose. So effectively I can put the x minus mu transpose on the other side, and because sigma inverse doesn't depend on the summation on little n, I can move it outside the summation. I can also divide and multiply by n, and then immediately what do you see on that big summation? I see the sample variance that I denote here as S. And now we have the trace of sigma minus 1 times the sample variance, and there is a formula that says when you differentiate the trace of AB with respect to the matrix A, the answer is B transpose. So in my case here, the answer is going to be S transpose, and S transpose is S because S is symmetric, and that's my second term. You put those terms together, and here is the final answer, that the MLE estimate for sigma is equal to the sample covariance matrix S, which is the anticipated answer. So a little bit of algebra, but I think it is useful to familiarize yourselves with it. This trick here is fundamental, but also being able to take derivatives of the logs of determinants and things like that is nothing difficult. And everything I mentioned today in this slide, they're using the formulas that you see on the bottom. These formulas have been extracted directly from an appendix from Chris Bishop's PRML textbook, and so you can consult them if you want to, or this slide gives you enough information for what you need. And if you want to really prove any of this, I am not going to bother to do it in this lecture. I proved two of those in this slide, so you can actually read it, okay, and see that there is no magic. And as I told you, an easy way to compute gradients with respect to the matrix, to a matrix, is take derivatives with respect to the components, and then put all of them, these gradients, put all of them together in the form of a matrix, and that will be the desired answer that is incorporated in these formulas. Okay, so that's the answer for the multivariate Gaussian. You can see the results written here, and I give you an alternative form, if you like, for the MLE estimate for sigma that involves the summation of xn transpose and the sample mean. And the reason I give you this expression, because often you may need to approximate this summation, and so you can see the summation, you can easily approximate it, you can write it in terms of the MLE sigma, and also x bar transpose, where x bar is the MLE estimate of the mean. So you can repeat the calculations we did for the univariate Gaussian when it comes to unbiased and biased nature of the mean estimator and the covariance. And the only things you will need, similarly to the univariate case, is the following two formulas. Actually, I put all the two cases here as one formula. If m is not equal to n, this term is 0. So E of xm transpose becomes E of xn, E of xm transpose, so it's mu transpose. And if m and n are the same, the second moment, E of x transpose becomes mu transpose plus sigma, because you remember the covariance is the second moment minus the expectation transpose, right? We're working with vectors here, so this is an analog expression to say that the variance in the univariate case is the expectation of x squared minus the mean square. Okay, this is written for the multivariate case. So again, this estimate is unbiased, and the MLE estimate for sigma is a biased estimate. Okay, so to finish the lecture today, let me tell you that often, and both for the MLE estimates and other estimators we will see for Bayesian analysis, it makes a lot of sense to be able to update estimators sequentially. So for example, the question would be, if you computed the MLE estimate for your first n-1 data points, can you update can you compute the MLE estimate for n data points by using your previous estimator based on your previous n-1 points? And the answer is actually simple algebra that I'm not going to bother about it. So let me denote here the MLE estimate with superscript n referring to my MLE estimator using the n data points. Okay, and similarly, I am going to call mu MLE with n-1 superscript my MLE estimator for mu using my first n-1 points. So if you follow this simple algebra, all right, nothing major, you can immediately see analytically that my estimator for n points is nothing else but my estimator for n-1 points plus 1 over n times xn minus my estimator for n-1 points. So effectively what I have is I have a correction to my previous estimator, okay, and the correction involves an error signal that is the difference between my data point xn and my previous MLE estimator for the mean. And then there is this coefficient on the front that I call it a learning rate. Now, so when you use this formula effectively, when if your interest is in computing the MLE estimate, let's say for mu, you don't have to keep track of the previous n-1 points, because the only information that you need to update and compute the MLE estimate for n points is to use your previous MLE, right? And again, this expression is exact, all right? Is exact. All right. So the question here is, can we sort of generalize this? Okay, can we generalize this type of idea? And the answer is yes, we can. For those who have taken other courses or maybe have looked at books on stochastic gradient descent, they may recognize this update formula as literally stochastic gradient descent, where you use some previous values of your parameters and some learning rate, and then this error signal is really a gradient or a negative gradient that drives the minimization of some loss function, as we will see. Okay, so let me before, since this again is going to be new to lots of you, let me introduce the original Robbins-Monro algorithm, and then I'm going to try to, at least with the Gaussian univariate case, to make some connections with gradient descent. So let's see how this exact formula can be reproduced using what is called the Robbins-Monro algorithm. So suppose that we have two variables, zeta and theta, and we have this red curve that I call the regression function, and we want to find the zero of this function. So we want to find the theta that minimizes this red function. Now the problem is that this red function is not known, and the only thing we know for different values of theta are some noisy observations of these functions that I denote here with this variable z. So again, we have this regression function. We want to compute the point where it becomes zero, but we don't really have, we don't know this red function. We only know a noisy approximation of this that is given by these blue dots that you see in this picture. So to compute the zero of this regression function is what came with this extremely impactful paper in 1951 by Robbins and Monro that is called a stochastic approximation method. And this idea literally has revolutionized the way we compute, the way we update parameters, let's say in deep learning, in complex neural networks, and many different type of problems. And actually I can tell you the method, we're going to apply it for MLE estimation, but the MLE, the negative log likelihood that you use in as a loss function in MLE calculations is a convex function. That is not going to be the case for many applications of these stochastic approximation methods. So this regression function that I mentioned is not known, and so we're going to assume that this regression function is nothing else but the expectation of these noisy measurements given theta. So again, we're going to look for the zero of this function, where we don't really have direct access to this expectation that defines the function. The only thing we have is noisy observations z. Okay, so this idea of noisy observations is fundamental. We need to be able, from example, from samples alone, to be able to sequentially compute updates for the parameters theta without having access to this red function. So how does the Robbins-Monro algorithm operates in computing the zero of this function in this setting? Effectively, to compute the zero, you iterate the algorithm that you see on the second formula. So you use your values of the parameters at the previous iteration minus some learning coefficient that may vary per step times z evaluated at the previous estimate for the parameters. Now, to make this to work, and this is part of the fundamental work of Robbins-Monro, you need to have some constraints in the learning rates, and these constraints are summarized on the three equations on the bottom. So as n goes to infinity, an has to be equal to 0. The summation of all of the ans has to be equal to infinity, and the summation of an squared has to be less than infinity. Now you may say these are too many strong constraints that these learning rates have to satisfy to guarantee that this algorithm will work, but actually later on, when you take courses on for example, on training neural networks, and you learn about what learning rates you're going to use, you will see that it is rather straightforward to guarantee that the Robbins-Monro conditions are satisfied. So for now, I am not going to say anything anymore, except this is what the Robbins-Monro looks like. And in the original form, the idea was to compute the zero of the function, and the zero of that function corresponds to this expectation of the z's. All right, so let me make now a huge step, okay, a huge step in making this algorithm relevant to computing MLE estimates in a sort of iterative fashion. So how do we compute MLE estimates, right? We have to set so here we need a function, and we need to compute the zero of a function. So in the MLE estimates, we need to take the negative log likelihood, that's my loss function, and I need to minimize it. So what is the function then that we want to find the zero? That function is the negative gradient of the loss function. So it is the gradient, is the negative gradient of the log likelihood. Does it make sense, right? You remember the exact estimate for the parameters comes by taking the gradient of the log likelihood and setting it equal to 0 and solving for the parameters. Right? And lots of times you're not going to be able to solve analytically because maybe that equation is non-linear. So the function in our setting where we want to compute the zero of that function is the gradient of the negative log likelihood. All right. So if you think the negative log likelihood as related to this regression function f, then you can use this formula here, where z, what is it going to be? Is going to be a sample evaluation of the negative log likelihood. All right, and this will be the MLE parameters that we update in the model. So let's see how the calculation goes, and then I'm going to give you a schematic that puts in a graphical way everything together the way I expressed them just a few seconds ago. So here is a Gaussian univariate, and I want to compute, let's say, the MLE estimate for the mean. So what I take is, I take minus the negative log likelihood, all right? This is my negative log likelihood, and I take the gradient with respect to mu, and I set it equal to 0. And remember, when you do the differentiation, the mu there is this derivative equal to 0 is valid for my MLE estimates, okay? So if I push the derivative inside the summation, I get something like that. And because in the Robbins-Monro, you remember the function was the expectation of these noisy observations z, so I need to put it in a similar form. So what is that similar form that I can do? I see here I have a summation over little n. These are my samples of 1 over n times that. So effectively, from the law of large numbers or from the central limit theorem, the summation of 1 over n times these values is nothing else but an expectation, all right, of this expression that you see here, which is the gradient of log of p evaluated at the maximum likelihood point. All right, so effectively what the z is in my case, right? So the z is nothing else but this negative gradient of the log likelihood, all right? Negative gradient of the log likelihood. And before I had noisy observations of z, now I'm going to have a noisy observations of this negative gradient evaluated at each sample point x. All right, so if you compute this for each sample point x, that will be a negative observation of this quantity that I call here z. So if you do that, right, so this is your z, all right, that's the negative gradient evaluated at the MLE. So if you take your Gaussian, you compute derivatives with respect to mu, and then you set mu to be the MLE estimate, what you get is minus x minus the MLE estimate divided by sigma square. Okay, so x is noisy, x comes from a Gaussian, all right, so this z follows also a Gaussian distribution, and this is my MLE estimate. I don't bother with sigma square at this point, right? So I take sigma square, let's say, to be constant. And if you like, my regression function, you remember, is the expectation of z under the distribution of the data. So if you take expectation of x, that is the true mean. So the regression function is minus mu minus the MLE estimate of mu divided by sigma square. So now can you see that actually the zero of my regression function is really the true mu, and this is what we really want to do, right? This is what we really want to evaluate. But we don't have access to this true mu. What we have access is to these noisy observations, and if we actually take the Robbins-Monro formula for the updating of the parameters mu MLE. So the parameters theta in the Robbins-Monro equation are now my MLE estimate for mu. So I'm going to have my previous estimate, all right, plus an update once I I see point xn. So this is my learning rate. And here what I'm going to have is, you remember in the Robbins-Monro formula, there is minus an minus 1 times z, computed at the n minus 1 estimate of the parameters. So minus and minus here cancel, and I get this error signal, if you like. And that's my update for the MLE estimate for mu using Robbins-Monro. It looks practically identical to the exact update formula that we saw before. As a matter of fact, if you want to literally make it to be equivalent, exact to that previous formula, the only thing you need to do is to place as a learning rate to be sigma square over n. All right? And you see, by the way, here that the learning rate varies as 1 over n, right? You can actually check that 1 over n satisfies the properties of the Robbins-Monro algorithm. And if you use this learning rate, effectively this update becomes exactly equivalent to the iterative update that I gave you before that was exact. Now, obviously, I am not doing this example of the Robbins-Monro algorithm because we're going to be calculating the MLE estimate iteratively for the univariate Gaussian, because we can do this exactly, but the procedure that I highlighted this may be very essential for problems where an analytical estimate for the MLE values of the parameters of your distribution doesn't exist, and in that case you need to use some optimization method to do the computation. And we now see that this Robbins-Monro algorithm is very handy in allowing you to do this type of calculation. So the only thing, again, that I remind you, and I think there is a schematic that summarizes all of these things. The original Robbins-Monro algorithm computes the zero regression function. Okay, so in my case, my regression function is literally the negative gradient of the log likelihood. That's what my loss function is. The negative gradient of the loss function, right? This is what you set equal to 0 to find your MLE parameters. The parameters obviously are mu MLE. This is what you want to compute. Mu is the true mean of your model, and the regression function, as I showed in the earlier slide, is minus the true mean minus the MLE estimate divided by sigma squared. We don't really know mu. What we know are these noisy observations z that you see here. All right. So effectively, at each value of the MLE parameters, this z follows a Gaussian. All right. Follows a Gaussian. All right. And the regression function evaluated at that particular value of the MLE estimate of mu is nothing else but the mean of z. So it is nothing else but minus mu minus your current MLE estimate divided by sigma squared. Again, this is your regression function, right? And this is the zero you want to compute. You want to find the MLE estimate that is equal to the true mean of your distribution. All right, can you do this for an iterative update for the variance of a univariate Gaussian? First, let me show you analytically. Here is the exact formula. So if you want to evaluate the variance when you have n points, you can use the estimate for the previous n minus 1 points, and then there is an update formula that again seems to have some error signal and some learning rate that is 1 over n. So how are you going to use Robbins-Monro? You remember you need to use as your regression function, right? You need to use minus the gradient with respect, in this case, sigma square of the log likelihood. So what you have to do is write down the negative log likelihood, take the gradient of that, all right? So we're going to have in Robbins-Monro there is a negative and minus the negative log likelihood. The two negatives will cancel, and then this is what you have in the this is your log likelihood, and this is the gradient with respect to sigma square. So when you compute this, this is what you get, and somehow it looks very, very close to the analytical form. Okay, as a matter of fact, again, you can make the two formulas to be identical by using, in the Robbins-Monro algorithm, if you use the learning rate an minus 1 to be 2 sigma to the power 4 divided by n, then the two formulas become identical. Again, we don't really want them to be identical. That's not the point we try to pass here, but the idea here is not to use these Robbins-Monro approaches when somehow we can compute analytically in an iterative fashion these MLE estimates, but to use these formulas when there are no analytical expressions and the underlying optimization problem that minimizes the negative log likelihood is a difficult stochastic optimization problem. And of course, later on, when we move to loss functions beyond negative log likelihoods, this type of stochastic optimization or steepest descent gradient algorithms will be very handy as well, and actually way much more popular than using them for the MLE estimates that we have seen in the last few slides. All right, let me finish by saying you can repeat the same things, and you can do this as an exercise for the multivariate Gaussian. So if you want to, for example, to write the exact update for the covariance iteratively, this is the exact formula that you get. And if you want to write this update using the Robbins-Monro algorithm, again, you will need to compute the negative gradient of the log likelihood with respect to sigma. And when you do this, you get this wonderful expression, and you notice inside parentheses, actually this formula is identical to the exact update formula. And as a matter of fact, you can make both the Robbins-Monro and the exact update formula to become equivalent by using a learning rate that is equal to this expression that you see in the bottom. Again, you don't have to put this exact update formula. You can use a learning rate that satisfies the Robbins-Monro conditions, and this formula will converge even though it is not an exact update, and usually it converges in very few number of iterations. Okay, I know we started with very simple concepts today of this maximum likelihood estimator. We discussed about biased and unbiased estimators. We extended things to the multivariate Gaussian, and then at the end we introduce this new idea of computing these MLE estimates or minimizing the negative log likelihood using stochastic optimization methods. So there is a lot of ideas there that you need to understand. Some of them may be useful in follow-up lectures, but I guarantee to you all of them will be extremely useful if you proceed in further courses in machine learning and deep learning. So please do put an effort to understand the significance of the concepts delivered with the lecture today. Thank you. Bye.